Welcome to this lecture on the fundamentals of biomolecules. Today, we are going to explore a fascinating and essential tool in biochemistry known as the Haworth projection formula. If you have ever wondered how scientists visualize complex, three-dimensional sugar molecules on a simple, flat piece of paper, you are in the right place. Let us dive in and build our understanding from the ground up. To understand why we need this formula, imagine you are trying to draw a complex three-dimensional Ferris wheel on a perfectly flat piece of paper. If you just draw it straight from the front, all the seats overlap. You cannot tell which ones are facing toward you and which are facing away. To fix this, you might draw the Ferris wheel from a slight angle, tilting it so the front seats are clearly visible and the back seats are tucked away. This is exactly the three-dimensional challenge chemists face with ring-shaped sugar molecules. Now that we understand the visual challenge, let us look at the solution. The Haworth projection is a standardized way of writing a structural formula to represent the cyclic structure of simple sugars, or monosaccharides. Named after the English chemist Sir Norman Haworth, this clever drawing trick takes a three-dimensional sugar ring and tilts it on the page. By drawing the sugar as a flat polygon, typically a hexagon or a pentagon viewed from a slight angle, scientists can quickly understand the shape of the molecule without needing a physical plastic model. Building on that tilted perspective, let us examine the specific drawing conventions used in these projections. To create a sense of three-dimensional depth, the bonds closest to the viewer are drawn with thicker lines. Then, the attached chemical groups, like hydroxyl groups and hydrogen atoms, are drawn on vertical lines, pointing straight up or straight down from the carbon atoms in the ring. This standardized format allows chemists to immediately identify the specific isomer of a sugar, based entirely on the upward or downward direction of these attached groups. You might be wondering why we care so much about these exact upward and downward directions. Understanding the Haworth projection is absolutely critical because the three-dimensional shape of a sugar determines its biological function in the real world. For example, the only difference between the starch in a potato that you can easily digest and the cellulose in wood that you cannot digest is the upward or downward angle of a single chemical bond. This projection is the universal language used by doctors and biochemists to design drugs and understand metabolic diseases. This brings us to the mathematical logic that allows us to translate a flat, linear drawing into this three-dimensional ring. The formula shown here represents the fundamental conversion rule from a linear Fisher projection to a cyclic Haworth projection. dH of x represents the final direction of a specific chemical group in the Haworth projection, which can only be up or down. dF of x represents the direction of that exact same group in the original Fisher projection, which is either left or right. The rule simply states that if a group points left in the linear form, it must point up in the ring. If it points right, it must point down. Before we move on, let us see this formula in action with a concrete example. We will convert the linear form of D-glucose into its cyclic Haworth projection. We start by drawing a standard six-membered hexagon with an oxygen atom in the top right corner. Next, we apply our conversion rule to carbons 2, 3, and 4. Carbon 2 and 4 have groups on the right, so they point down. Carbon 3 has a group on the left, so it points up. For carbon 5, because it is a D sugar, the bulky CH2OH group points up. Finally, for the alpha form, the carbon 1 group points down. giving us our final structure. Now that we have used this rule to draw the alpha anomer, let us understand the logical reasoning behind that final step. When the linear sugar curls into a ring, carbon 1 becomes a newly formed chiral center, known as the anomeric carbon. In D sugars, the terminal CH2OH group on carbon 5 always points up. By definition, drawing the alpha anomer requires the hydroxyl group on carbon 1 to point in the opposite direction of that carbon 5 group. Since carbon 5 points up, carbon 1 must point down. This logical deduction ensures the three-dimensional geometry is perfectly preserved. Let us visually reinforce what we just learned and proven. On the screen, you are looking at the complete transformation of D-glucose. On the left is the linear Fischer projection, showing the exact left and right positions of the hydroxyl groups. The curved arrow illustrates the oxygen on carbon 5 attacking carbon 1 to close the ring. On the right, you see the resulting Haworth projection. Notice the thick lower bonds creating a sense of depth. You can clearly see the alternating up and down pattern of the hydroxyl groups that we just derived, perfectly mapping the stereochemistry into a flat drone view. Having mastered a six-membered ring, let us shift our focus to a slightly different type of sugar. Fructose is a ketose sugar, meaning its reactive carbonyl group is located on carbon 2 rather than carbon 1. Because of this structural difference, it forms a five-membered ring instead of a six-membered ring, known as a furanose ring. This is a crucial exercise because fructose is the primary sugar found in fruits and honey, and its specific three-dimensional shape is exactly what dictates how sweet it tastes to our taste buds. Let us apply our conversion formula to this five-membered ring by converting linear D-fructose into its beta anomer. We begin by drawing a five-membered pentagon with an oxygen atom at the top. Looking at the linear form, carbon 3 is on the left, so it points up. Carbon 4 is on the right, so it points down. Because it is a D sugar, the terminal group on carbon 5 points up. Finally, to make it the beta anomer, the hydroxyl on carbon 2 must point in the same direction as carbon 5, which is up. This completes our structure. Let us break down the mathematical reasoning behind that final step for the beta anomer. In fructose, the anomeric carbon is carbon 2. This carbon is unique because it holds both a hydroxyl group and a CH2OH group from carbon 1. The rule for a beta anomer requires the anomeric hydroxyl to point in the same direction as the carbon 5 terminal group. Since carbon 5 points up, the hydroxyl on carbon 2 must also point up. Consequently, the other group attached to carbon 2 is forced to point down, preserving the exact stereochemistry. We have covered a lot of ground today, so let us summarize our key takeaways. First, the Haworth projection is an indispensable visual tool that bridges the gap between flat chemical formulas and complex three-dimensional biological structures. Second, the conversion rule is simple but strict. Groups on the right point down, and groups on the left point up. Finally, the orientation of the anomeric carbon determines whether you have an alpha or beta sugar. Mastering this projection is your key to understanding how simple sugars link together to fuel all living organisms. Great job today.